Welcome to Coloured Flames. In order to observe coloured flames, you will need the following materials. Several metal chloride salts such as strontium, lithium, calcium, sodium, copper and potassium. You will also need ethanol, 6 beakers, 6 watch glasses, a long neck lighter and forceps. Let us have a quick look at the demonstration. The left is the flame of lithium chloride, while the one on the right is potassium chloride. Do you ever wonder why do different metal salts have different flame colors? Visible light is electromagnetic radiation that can be detected by the human eye. Electromagnetic radiation has a dual nature as both particle-like and wave-like, where the particles move in a wave-like manner. The longer the length of the wave or wavelength, the lower the light energy, whereas the shorter the length of the wave or the shorter the wavelength, the higher the light energy. The electromagnetic radiation has a wide range of possible wavelengths within the electromagnetic spectrum. Within this electromagnetic spectrum, only visible range 400 to 700 nanometers in wavelength can be viewed by the human eye. Red color has the longest wavelength, which means it has the lowest energy, whereas violet has the shortest wavelength with the highest energy. If we break down any substance, it is formed by atoms. Atoms are composed of neutrons, protons, and electrons. Neutrons and protons stay in the nucleus of the atoms, while electrons move around the nucleus and form the electron cloud. If atoms lose electron or electrons, they can form ions. The lithium cation, Li+, which has lost 1 electron, has now 4 neutrons, 3 protons and 2 electrons. It has 2 electron shell, where the outermost shell is free of electrons. The potassium cation, K+, which also has lost 1 electron, now has 19 protons, 20 neutrons, and 18 electrons. There are 4 electron shells in potassium, where the outermost shell is free of electrons. When heat energy is applied to the metal, such as from the flame of a long neck lighter, the electrons absorb the heat. The electrons become active and unstable, and the activated electrons will jump to a higher energy electron shell, which is further away from the nucleus. However, because the electron is unstable at the higher energy shell, the electrons will then preferably return to the lower energy electron shell, which is closer to the nucleus. There are several pathways for this. Each of these transitions involves a specific amount of energy being released, which corresponds to the energy gap between the electron shells. This energy gap relates to a particular wavelength and hence color. The relationship between wavelength and the energy gap between the shells is stated by lambda, which is wavelength, equals h, which is Planck's constant, times c, which is the speed of light, divided by delta E, which is the energy gap between the shells. As a result of the combination of transitions, light of various energies and wavelengths are produced, and the color you see is a blend of these. The exact energy gaps and wavelengths of the possible transitions vary from one metal ion to another metal ion, which is why different metal ions have different flame colors.